So, I used to have human development for then I also I uploaded on that second stuff. Oh, absolutely. Check. Oh, that's true.
Thank you everyone for coming to this colloquium today. We have a distinguished visitor, Prasenjit Saha. Prasenjit did his master's in IIT Kanpur, and before he moved on to do his PhD with James Finney in Oxford. And then after that, he did a number of postdocs in Rutgers, then Toronto, before coming back as lecturer in Oxford, then UMU in London. And then after that, he was not in a potential well in Zurich. He loved the place there, so he stayed there. Prasenjit has been working on a number of things related to galaxy dynamics, but also has ventured into gravitational lensing, and he loves to explore new topics. So today he will talk about this new thing that has been interesting him for quite some time, but now also maybe something that can be realized in observations. So he will talk about the Hanbury Brown Twiss effect.
Thank you for the kind introduction, and thank you for hosting this visit to this beautiful and unique campus. Um, so let me talk about imaging the unimagable. Well, my talk is two parts. The first one will be actually explaining the dynamics. So I'll explain what I mean for the purposes of this talk by imageable and unimageable, and I'll try to explain what the Hanbury Brown effect is. Try to explain it. That's the first part. And the second part of the talk is why we care. And gradually move from the first part to the second part. So I need to explain the title. What do I mean by imageable and unimageable for the purpose of the story? Well, let me show you a little animation based on inspired by XKCD. There's an XKCD item called height. Just look it up. You don't find this thing here. But which plotted on the horizontal axis, sorry, the axis levels of forward, is plotted these spots on the horizontal axis, and on the vertical axis, we plotted the distance. So 45-degree line, any 45-degree line is constant angular size. So we start with an observer who has been observing this place for a very long time, and then the fluids are like planes are like 1 kilometer up. At the top of the atmosphere, where you can see an aurora, is like 100 kilometers. That's where kind of astronomy begins. Now, what I'm going to do is zoom outwards. When you zoom outwards, kind of think of zooming out. Now, this is one pixel on a 4K screen. So zooming out by a factor of a few thousand. And if you do that, we get to a little beyond the moon. So this is the Earth orbits all. And that that line over there is a milliradian. It's an angular size of a milliradian, which is roughly the annual resolution of our eyes. Then, if we go to the left of that, so much there, I just put in Phoebe, like, and so on, imaginary of the Earth, which I won't explain now because ask me. But if you go a bit to the left to more smaller objects, we get this one, but we get the International Space Station, which is just a little bit too small to see with our eyes. We can see just fine. There's fainter line out here, it's easy. Sorry, so faint, but it's somewhere here. It's a line which is a microradian. And a microradian is about the annual resolution of a telescope. This telescope a bit less, a bit more microradian. Space telescopes, so the other JWST on top, and then there's a satellite, one of the navigation satellites, I think. So with our eyes, we can only see more. With the telescope, we will see the International Space Station. Any other artificial satellites. But if you have a telescope, you can see all the planets very light. So with our eyes, we can just resolve the sun. But with the telescope, we can make it. It's perfect for the sun. That's why planets are simple. So I've now zoomed out times by a factor of 1,000. Let's zoom out yet again by a factor of 1,000. Then we get to the transception zone, where everything is too small to resolve. We can't resolve anything. There are pictures of there on Pluto and one of something else whose name I can't recall this now. Those are extreme stars which are here there. There's lots of stuff here we don't know about. Extreme discoveries. That's a topic for another talk. Now another zoom by a factor of a few thousand. Now nothing can be resolved by a telescope, right? Because that microradian line is out here. So stars, bright stars, even the closest ones, little points of light. And if you go to the left, left there is even smaller things which are non-stop, like white dwarfs and brown dwarfs, which are smaller, even more difficult as well. And zoom out again. Then we get to the local group of galaxies, and now things get bigger again. Size because here's the up here. So there are things we can resolve quickly. They're mostly very faint, but we can't resolve. So out again. We haven't zoomed out, we've gone to the left, got really small objects. But there is the current smallest in angular terms resolved object, which is the special purpose. Let's do this. Zoom out again. The last of our zones. And there we are. There are again some things which are bigger than a milliradian, which are can be resolved with our naked eyes. I think to the right, left things we can resolve with a telescope. And notice that this 45-degree line kind of starts to curve. That's inflammatory distances. And for nerds, what we think here is you're all nerds, but anyway. Since you asked, let's look at. So very summary of the science of the universe, and that's milliradian, and that's microradian. So what astrophotography happens here? a lot of probably the astronomy was from involvement comes here. This is the band over here is things we can see best. This is you can see it even more easily, but there's not that much there. Right? There's a whole lot of stuff waiting to be discovered. If you can push this little resolution from here, it's fun. So that's immeasurable, is hard, unmeasurable. So how do we do this? Well, there are very specialized techniques. Talk about is something I first learned from just in the volume 3 exercises. There is an exercise which tells you, okay, there's no time to explain it now, but kind of tells you to imagine two stars and two detectors. And the detectors look for two photons coming simultaneously from two sources. So you know this time emitting the photon, this time emitting the photon. You know this time detecting the photon, this time detecting the photon. But you don't know which detector detected which photon. Right? The two possibilities. And because those are indistinguishable, they will interfere in concepts. So the probability of detecting the two photons simultaneously is the interference of these two amplitudes. And if you're looking for detecting bosons, you detect the plus side. If you're detecting fermions, that's the minus. So, the exercise here is to work out. And it was a very nice feeling, right? Nice touch. But let's think about it another way. And here is an experiment, an experiment set up a couple of years ago by my collaborators. Me too, right? And isothermal, then that isothermal nowadays. And what she did was just modify a microscope interferometer slightly to put a little, it was like a beaker of water with some turbulence to mess up the coherence of the And what you observe when you do that in the straight fringe wall of this undergrad experiment with a slight modification is kind of a step back. Take a movie with a smartphone and you autocorrelate. Magically, the fringes come back. So that when you autocorrelate the individual frames in that you recover the interference pattern you were looking for. That's the way of thinking about it. So let's continue that explanation in another animation. Here is here's a tweet from a few years ago. It was meant to be a joke, and just when JWST went up, it said, no, so JWST has produced an image of Proxima Centauri. And this is what it looks like. And now, GWST, not much Proxima Centauri is. Orders of magnitude to the left. So, and people started taking this seriously. Okay, you'll have to look up what this really is. It's a topic. But let's for a moment pretend that it is. And imagine something of the size of Proxima Centauri, 1 million seconds across. Think of the photon flux. Now,
May I ask you a question?
yeah, go ahead.
So, like, when you say this autocorrelation, so like there are several photons in this spectral pattern. So, how do you autocorrelate all of them together? This is like a really very complex problem. And then, is there any boundary conditions or you?
question is how we autocorrelate the spectrum. So these were literally autocorrelating the images, which is straightforward. Taking the images and taking the autocorrelation of each image, each frame, and then averaging the autocorrelation.
So you have multiple frames and then what?
Each frame we autocorrelate. We don't have autocorrelate.
Okay, so each
Individual frames. The correlation is spatial.
in that autocorrelation, do you have any like boundary conditions so that you are getting back the main fringes?
So we put this to a usual correlation. Okay, like this. And then we average for lots of frames. Often, right? If you average the frames, if you just average the frames, you get uniform illumination. If you average autocorrelation, okay, maybe it will become. So here is the photon flux that lying on the ground if Proxima Centauri were a giant laser, which of course it isn't, but let's imagine that it is completely covered. You would get essentially any photograph. Now, suppose we, if you're thinking of it as a single laser, we think of it as lots of lasers with a slightly different frequencies. So we gradually go on the phase. Now let's gradually let it go. Let's see what happens to the battery. Right? It breaks. And it turns into this speckle pattern. And so you see these speckles coming and and the narrower frequency pattern, the longer these. Now, in the lab experiment, it was possible to take a picture of these speckles from Proxima Centauri or in the star we can't, because look at the photon flux. It's less than 1 photon per square kilometer. So it's less than 1 photon per bright speckle before the speckle is finished. Right? How if you can't follow it up. The probability of getting a photon from one of these bright fringes or speckles is only quite small. The probability of getting 2 photons from the same bright fringe is even smaller, much smaller. It's not zero. Occasionally it will. So if you look for pairs of photons, very occasionally you will pick up 2 photons from the same fringe. In fact, 2 photons will tend to be from the same fringe. So what you do is similarly you look for coincident photons that are near distance. The coincidence probability coincidence photons of a given distance for many different distances. So not the photon flux, but the coincidence probability. Now, if we so time averaging this, we get this pattern, which is the correlation of it's not an image of Proxima Centauri, it's a correlation to economic because but that's a problem. And then this is the Hanbury telescope systems which has been used to do this type of experiment, not with Proxima Centauri and newer stars. And if they hit the detectors, which were red sensitive, they would be looking at, well, this is the fringe pattern from the correlation pattern from the Proxima Centauri usually, except I've taken one so you see this very fringes. And though the positions of the As telescopes are fixed, the Earth moves. So you do this UV plane sampling, like friends same technique. This is what the sampling you get from the Harris telescope. So if they had the newer generation detectors, they could measure the radius of star. And but they couldn't measure the structure. So let's look at go back to the structure of this thing, which is not of favorites. And let's look at the um, let's say we have a collection of light detectors, which are the Chekhov telescope array. And we equip it with well, the detectors will be there anyway. And there's a coincidence for once using these telescopes. Then here's what here's the signal from Centauri, right? And so this is Proxima Centauri rising and then setting, and because you've got a lot of telescopes, beautiful sound UV plane. So that's the Hanbury Brown effect. I hope we're starting to see why we should care. Now, let's move on to more XKCD inspired institution. Now, this applies to any research topic really. It's the difficulty versus the excitingness. So the difficulty is where difficulty is proven is when we have plans is when somebody is funding to do it. Challenges is when there are simulations where everybody goes for it. Yeah. And dreams is we think we can do it, but there are we don't have control. Right. Then that's the difficulty. Then there's the interesting mistake. Publishable is you can publish it. Exciting is publishable, but it will get cited. Also is even also is people even outside specialties from it's my point when you really new stuff end up creating a new stuff right. So we know what on this so let's see where the science cases occur. So I'm thinking of a bunch of science cases, which is all together in groups. These. So the first bunch of science cases just measuring the radius. Right? And that was demonstrated by Anderson and Pease in 1920 for Betelgeuse and later. So and now people are talking about people are seriously trying to measure the radius of Sirius. So that's the plans involved. Kind of degenerated quantum system and everything. Then, so if you look at the potential targets, here are the sources versus the fields, which is important for a device for stars with second magnitude will be nice interactive. And if you go microstars, that's what you see. And this is the same set of candidates. Start to see the project domain sequence. The other ways was very interesting. There's here the multitude interferometry can cover the set very well. The next kind of science cases are things which are varying in a simple way. So binaries and this is alpha neo. The often alpha is the price started to spike up on speaker. And it's binary with a period of 4 days. And here is the same 4 S telescopes that I talked about. So they're very nicely resolved. Hanbury Brown and this, it's very dimensional. Measure this format. But now, they were operating at
This is a video for a energy telescope.
okay, so a high energy telescope, so this would be an optical wavelength. But the high energy telescopes look for gamma rays by looking at Cherenkov showers. So the original source of the shower are high energy, but the shower itself is optical. So the data you just use the set, you just use the different form.
Usually their telescope convention are not that good, right? They don't get a very good image quality.
That's fair. Image quality absolutely sucks, but it's better than what it is for in this case.
Your intensity
For intensity interferometry, you can use really bad. You can use the really bad. Not now, it's good if you have optical quality mirrors because you suppress the noise back. Also, the finishing maximum so these general things will be limited to one. Now, but there are also more exotic binaries. Now, but I don't need to explain what these guys. Yes. But so Lisa has these. There are these things called Lisa clarification binaries, which are binaries in the galaxy, which whose emission of gravitational waves would be so powerful that Lisa would measure them. So that's how you would test that Lisa is working. Right? And one of the things that Lisa would measure is the polarization of binary. So if the binary isn't, so those are the H plus H plus modes of you see this one is almost in this kind of orbit. That's why the H plus is very active and this one is not doing very much. If you had a different orientation, the correlations would be different. If you have this polarization, this one, this one. So these are the measures. If you can resolve the binary, so right now we know that there's a binary there, but we don't know the orientation of the orbit. If you measure the orientation of the orbit, you can test the orbit and have a prediction for the polarization. So that's general. That's one of the So we have features on the surface. Next category of things is we have features on the surface of stars whose well, whose shape we know theoretically, and starting with electricity, which is being demonstrated now, which is actually and these various features. An example of it would be or oscillation. So here again is something what should be done from oscillation or be done base, which is a general telescopic only. Even though it's a single dish, according to principle split into 4 dishes, really bright star with lights, which move very much on the sky. So it's a star. And then on the UV plane, you see things like this. In different pairs of telescopes, and you could, in principle, reconstruct the changing radius of which these are speculations, of course, but it looks in principle. Another example of a process called gravity darkening, which is with a rotating star, and so how much the pools that it's freedom. So the equator is far from pools, and it has been resolved. Okay. Yeah, these are images with microscopic interferometry. But of course, we don't think there's any interferometry as well. And slides, and even with I think things which are currently working, use check out of the source. Do that.
So actually, like taken by the signal.
Oh, the left, no, that's simulation. This one is reconstruction from microscopic interferometry. This one is simulation.
Why do you have a sharp arm?
Simulations.
That's actual on the microscope.
Oh, what? Oh, for the microscopic interferometry. I think it must be the one that I constructed. Yeah. So, so we could do a parameter reconstruction again. This was simulation. And then, okay, everybody has to use generative AI these days, and why not for intensity interferometry? So we're experimenting. All these simple systems have been parameterized. You can. Okay, now we come to features of unknown shape, where you really would need to do image reconstruction. That would be the idea of things like new image reconstruction algorithms. And then we have things like convective cells on star. Now the sun has several million small convective cells, but from theory, it's expected that on a giant star there would be just a few convective cells, which would be very large. I mean, each of these is bigger than the sun. This has been done again using microscopic interferometry. It's so far not attempted. This is the 1970s theory paper by Norwich, which is it's phenomenal. It's still kind of not seeing intensity interferometry is able to attempt yet, but it's a future. It's a future plan. Exoplanet atmospheres. One thing is you can measure the radius of a star, which is the next planet. That'll tell you the size of the planet. But more fun would be to resolve the planet itself, the shadow of the planet itself. So here is really, well, real planet is like speculative, because why not? If you look at the signal difference between the on-transit and off-transit case. In on-transit case, you need the signal is a few percent of the transit case. The signal is a few percent of the off-transit case, so you need a lot more observation. But I think with software linear simulation, it looks like it's doable. It's kind of a chain of okay, accretion and outflows. This is a super exciting topic. I'll just mention it because don't have to. But there are lots of things to know. And compute last set of applications and featured into one, including some updates just a couple of weeks ago. Talk about non-image problems. There are two of them, which one is to look at laser lines. Now, I said that the Hanbury Brown and Twiss effect applies to things which are not lasers, right? Or as superpositions of lasers with slightly different frequencies. there are stars, in particular Eta Carinae, which have lines which appear to be laser lines. And once again, the Togoba reviewed 1 plus this theory mechanism for producing these laser lines. And what an explorer of this would be odd. Let's see that this is a prospect of finding something called random lensing, which is a quantum-optical effect, which well produces very non-classical photon emissions. So finding quantum phenomena in an astrophysical system modified, but it's still in the super challenging area. Finally, we come to one which will take some time to explain. So, quasar-maculates. Now, this is a lensed quasar, one of the best known ones, one of the highest best ones. And here, in the middle, we've got the lensing galaxy. Here are 4 images of the same quasar, right? Now, but each of these 4 images is itself made up of lots of little images. And that's because the gravitational potential that produces the lensing is granulated by stars, granulated by discrete objects. I mean, dark matter is made of primordial crystal, primordial black hole, whatever. Stars that really don't exist. The other things, those ones are. So we know that the micro images are formed, and we know something about their properties, but they're on the kind of nanoradian scale or sub-nanoradian scale, micron scale. So nobody even thinks about recalling. But we solve them at least in a statistical sense. So let's look at that. This is some work with Ashish Meena, simulations from visiting about how Mexico, and one for this. Now here, for those who are not lensing nerds, how many are lensing nerds? So you know what this, right? I'm not patronizing you. These are the caustics. So these are the notional places in the space plane where the number of micro images changes. So when this quasar will continue regionally in the sense of maybe solar system size or something, and cosmological distance, when it crosses this thing, this acoustic, the number of images will change. And then now let's look at the image plane. And here we're looking at the potential. These are numbers of constant virtual like dynamic, and there are lots of these very complex structure, and the critical curves which are the constants about the image field. But when that caustic crossing happens in the source plane, you see this new pair of images appearing, very bright pair of images appearing, and then when it crosses to the other caustic, then this pair of images. Now we know this happens because these lens quasar images suddenly show large brightness variation. What is those extra microphones? So we know this phenomenon is going on. From theory, you have an estimation. We know let's look at it in the interferometric UV, right? When the thing changes suddenly, it's not a glitch in the simulation, it's the caustic proceed. Right? So these are the estimates of the photon flux that would and what range of signal to noise suggests that with next generation detectors and a large baseline like several kilometers, this effect will be detected. I don't know if it deserves to be on mind blowing apparently, but it certainly dreams and expression. So those just show this simulation of along the full simulation which actually made, and you see several caustic crossings happening. This the whole length of the simulation is of order 500 years. So, but this is for outermost of the images in the case of the pressure constraints. The images which fits in the see both one it's a population of stars. Images far. And anyway, you pick up optical layers. These subjectives in the and again, this will be in the awesome and dreams category. If given this given the rate at which you detect this, I think they will stop reading about it at least. So my summary slide at the end is lots of science cases and the development of detecting technology is taking things to the way. I think we will see quite a lot of some of these move into the problem region or perhaps in a couple of years. These will take longer. I think all of these arguments will move away this part in the medium term. Okay, so thank you. Please.
Questions for So I have some, maybe I can ask and then we can get started. So can you talk about the detector technology that is required in order to get this to the possible regions? And what currently exists and what you expect in the future?
So the traditional technology goes for which then the two technologies coming, which have come up now. One is avalanche photon effect by stable. That's solid stable process. A few microns inside the rings, and the probabilities are raised of them could happen. People frames, right? Thousands. Those a single photon comes, those have response times. Are still crazy. And they're more sensitive. Whereas the cubes and assumptions. So those are they have been there. There are kind of almost to be solved regarding the deployment of very small pixels and navigable lighter. But basic technology is indicate a very large variety of these spans. Other technology, which is the superconducting nanowires, these are going to have superconducting. It works three temperatures, superconducting, not really big wires. So you need liquid helium. That's what. You have wire coming regular wires. When a single photon comes, it briefly increases. So you can deliver it. And those have resolution stuff to things. Again, these architectures are getting large for sensitivity. It's a matter like the same issue is not studio making large frames. So I didn't talk explicitly about the signal to noise, but the signal to noise depends on, well, it's a product of this phi thing times the area. So for these super faint things, these are like 10 to the minus 10, like 15 minus 15 to the 10 to the minus 10. If you've got something like ELT, maybe times the area down to 10 to the minus 7. So that's the phase space impedance. Then times the square root of the number of wavelengths you want. So that number would go up 10 to the 14.9.
So this is like per given time interval, and then how many picoseconds or whatever the time resolution is.
So the key is to get this product. Let's see how much
For the
few more than one.
Yeah.
So well, bright stars, it's pretty fun. It's so serious if you got even an algebraic telescope, like one of these state of the art declavities. So and you got these state of the art, this will make you forget, probably minutes telescopes. What's the optical telescope? So yes, it would be fun to do it.
So compared to the early experiments, these targets are going to be relatively faint in the background, right? Look at all the objects in that location. Unlike your brightest star, so you don't have to worry about phase correlation or intensity correlation from other objects, but they are going to be like a noise. Yes. But in this case, you may have to mask to identify. For example, if you are going to do this 2237 plus.
So you need a telescope which makes the targeting to price. So
But you make all of them better. Right?
oh, but
Yes.
so you
So it's basically a question of made-up view versus
yeah, but you don't have to use the whole field of view, right?
basically regular and coming through. So you can put a state or mask versus state, which picks only that. Then that means that you cannot take a Cherenkov kind of telescope. But that's also very.
So the Cherenkov telescope.
And the third problem is even though it is gravitational lens, they are around 16, 17, 18 max. So if you want to take a nanosecond readouts or microsecond readouts, leaving it for photon.
Yes, you are not really go. You are photon time. So you don't care how, I mean, you don't need a photon to be there in your so it's you wait for the photon without when it comes you
You will not be affected by these statistics related to, because you are looking at correlations.
you check correlation saying statistics is important things in different way of because you're not really so, you're not really
Because you are also saying that you will limit your wavelength range. Your broadband width or not.
so you would set
Because too much constraint on.
send the different optical channels to different exposures and correlate that, right? That's all. Yeah, okay. The goal is to get 1,000 channels. Let's see. Let's see how much comes here. So that we place either copper.
So the like broadband, you will divide into smaller chunks.
That's right. Yes. Independent range.
What's the absolute field of view for it?
So the field of view, so you can narrow the field of view to down to the PSF of the telescope. Right. And you can even use, I mean, there are things, I mean, probably for something like this, you probably won't observe all four images at the same time at design and kind of have independent. So you want to do everything which is the main field of view of the telescope and play on. You have to design the instruments like
So even like you need to have the optics such that it will focus at the so that is like I think that's yes flow.
No, but now you start with that, we found the
Yeah, so
So to be it's a parameter with plenty maybe interesting things to that. Well, what he's saying, okay, it's current of plus. Yes, every so bad you are mixing up all the intensities, right?
someone who refer to current rates.
yes, why not?
Forget clearly isn't there going to be a telescope with a area of 5 times 6.5 meters square somewhere?
This is the analogy.
So if a large telescope, if a large, I mean, a telescope doesn't care whether it's continuous or not. If a different segments of it,
No, question is whether you have to segregate images. If it's a single object, I think I completely with you. Take one star and you are doing this. This can happen. We just collect the light and you have to transfer.
oh yeah, but these things are one thing. You have an array of which array is fast. So you just look at this. You look at this fast, which is you have one square trained on this, one square on this one. You look at it. You look just those pixels which are on it. Now you go okay, a bit more complicated.
And the segments of all the
Yeah. Now you also want to disperse it, so you want to spread it out in wavelength, and you want one bunch of pixels to look at my image, another bunch of pixels. Optical challenges to be solved that but something.
We talked about that you could measure now the size of a star. So this again subversive point is a few these exercises. What do I know is the right side?
Oh, sorry, say that again.
When we said that we can now images even the star, and we can now measure the size. What will the brighter? How do I know what I'm measuring the right side? What am I measuring?
I think people are extremely happy to get the fringes, right? From the correctly. And from the fringe you get it. I think this is
How do you know?
1990s, right? Kind of a fringe.
So my question is different. Yeah, I mean, so if you go back to my it's very good. So how do you know that you measure yeah. So
Size is okay.
so to leading order you just met, okay. What people are doing now is just measuring equilibrium test. But when you start to get slowly, of the UV plane, you start
First,
yeah.
what's the these spotted in the kind of what
Yeah, yeah.
no, it's not, it's moving, yeah, it's totally moving. So really, this I think that would test case because we know it's there, you have reason like this is easier than the sports and
the spot contrast will be better. Here you are talking about 1 to the 4. The area covered by planet will be smaller.
for if it's a giant astronomy.
And there will be always there. It is like not like outside the plane kind of mass.
Okay, any more questions? Well, if not, then let's start proceeding again. Prasenjit is going to around talk about an having please if you want to touch it. Please. Thank you. Yeah, exactly. What is it going to take?
Nice.
Yes. Could it also? I also learned recently from me about this exam. After working in the same Okay.
That is one of the arguments. And you are good, right? For life is very okay. What kind of market you take?
Okay. It was based on this.